This is example 8.5 from Discovering Design with Chemistry. A chemist burns 75 grams of an unknown substance. The complete combustion produces 85.7 grams of carbon dioxide and 43.8 grams of water. Nothing else is produced. What is the empirical formula of the substance? So let's just think this through what's happening here. So we have some unknown substance. We burn it, so we've got some oxygen going on there. And then we end up with some carbon dioxide and some water. All right, we know from the problem that we have 85.7 grams of carbon dioxide at the end, and that we have 43.8 grams of water at the end. We can use that to figure out how many moles we're using in this. And of course, in this particular problem, we don't know how many of each that we're using here. And that's not important to what we're doing, but I'm just making a point. This is not like a balanced chemical equation or even a complete chemical equation. It just helps me to keep track of all my pieces if I kind of write down what I have going on here. So this is our unknown substance. Okay, so what we're going to do is we know that these things work in moles best, and we're able to convert between one or the other. So let's figure out how many moles of carbon dioxide we have and how many moles of water that we have. The author assumes at this point that you can figure out how to find the grams per mole of carbon dioxide and that of water. So I am also going to assume that you know how to do that. And so 1 mole of carbon dioxide, I'm going to use colors again, is the same as 44.01 grams. So if we're going to convert the carbon dioxide, we start with our grams that we're given, and then we set up our conversion relationship. When we divide, we get, I suppose I should show you that part. I was going to just skip straight to the answer. When we divide, we start with our 85.7 divided by 44.01. We have to limit it to 3 significant digits, so that's 1.95. So we have 1.95 moles of carbon dioxide, and that's carbon dioxide as a set or as a whole molecule. And because moles are just a way of counting things, that means we have 1.95 moles of carbon, and we also have 1.95 moles of O2. And this is the important one, the carbon one, and we'll come back to that in a minute. All right, so let's go on to the oxygen one. I mean, not the oxygen, the water. So now we're going to deal with water. Again, we're going to assume that you know how to calculate that. So 1 mole of water is 18.02 grams. So we're going to use that to convert our 43.8 grams of water into moles. So 1 mole of water is 18.02 grams. Our grams cross out. Sorry, I should have crossed them out up here too. And when we divide again, we have to limit it to 3 significant digits. So we have 43.8 divided by 18.02, and that gives us 2.43 moles of water. Which means we have 2.43 moles of H2, and we have 2.43 moles of more oxygen. All right, so now that we have those numbers, let's move my problem over so we can continue to see the problem as we work it over here. So now that we have those numbers, we can start to see where we're going. This original thing that we had over here, because it was complete combustion and nothing else was produced, we know that this box has to be made of the carbon and the hydrogen and, spoiler alert, possibly oxygen, but definitely carbon and hydrogen. And so to move forward with this, to figure out what all it includes, all we know is that we have 75.0 grams of whatever that one was. I'm not really sure why I wrote it up there. Let's write it down here so it matches the others. So let's go ahead and figure out how many, I know we just converted from grams to moles of the whole substance. But let's convert back to grams of just the carbon and just the hydrogen. Before we do that, I'm going to put the hydrogen into not just H2, but just H, like just hydrogen. So if we have 2.43 moles of H2, we need to double that to get just the H's. So that would be 4.86 moles of just hydrogen. So now let's convert this to just grams, and we can do it the same way we did before. We start with the 4.86, and let's put our unit, moles, and then for hydrogen, for every 1 mole of hydrogen, we have 1.01 grams, and that just comes right off the periodic table. And so when we multiply those two numbers together, 4.86 times 1.1, we get 4. Blah blah blah. We can keep 3 of those significant digits, so 4.91 grams of hydrogen. We're going to make sure we kind of keep track of this number, so I'm going to put a squiggly box. That's not our answer, that's not where we're going, but that's an important number that we'll need in a minute. For the carbon, we're going to do the same thing. We have 1.95 moles of carbon, and when we want to convert the moles to grams for carbon, we have 1 mole for every 12.01 grams. And again, that's just right off the periodic table. 1.95 times 12.1. So we have to keep this one to 3 significant digits, so that's 23.4. So that's how many grams of carbon we have. So 23.4 grams of carbon. All right. So we know how much hydrogen is in that original substance, and we know how much carbon is in that original substance. And because of the conservation of mass, we know that if we add those 2 gram amounts, we can find out if carbon and hydrogen are the only 2 in there, or if we also have to account for some of the oxygen being in there too. So let's go ahead and add those 2 numbers. So we have 23.4, that's how many grams of carbon are in there. And then we have 4.91, that's how many grams of hydrogen are in there. And when we put those together, we have 28.3. I know it says 3.1, but we're going to call it 28.3 because our carbon had its last number in the 10th place, and so our answer can only have its last number in the 10th place. So let's see, where do I want to write this? Just going to keep moving the problem over so we can keep working sideways. So when we put these 2 together, we get that there are 28.3 grams of carbon and hydrogen in our substance. But we know that we also have more to it because we have 75 total grams. So when we subtract the 28.3 grams, what's left must be the grams of something else. And in this case, the only other thing that could possibly be would be our oxygen. All right, so let's subtract these 2. All right, so we have 46.7 grams of oxygen. We need to know that in moles because over here we found, let me use a highlighter, this is how many moles of carbon we have, and this is how many moles of hydrogen we have. So like in example 8.4, where we compared the number of moles of each that we had so that we could figure out the ratio between them to get the empirical formula, we're going to do the same thing again. So we still need those moles. We converted to grams just to see if they were the only thing in the unknown substance, but we don't really need the gram numbers for carbon or hydrogen anymore. Now we need the mole numbers, but we never found the mole number for oxygen, so now we have to convert how many grams of oxygen we have to its mole number. So we have 46.7 grams, and we need to convert it to how many moles that is. Again, this is just coming off the periodic table, so for every 1 mole of oxygen, that's 16 grams. So 46.7 divided by 16.00. So for this one, we have 3 significant digits, so 2.92. So that's how many moles we have of oxygen in the substance. We have more moles of oxygen in the oxygen that we burn, but we don't care about that because that's not what we're working on here. So these are our 3 numbers. So I'm going to collect them all to the same place. We're going to move this down a little bit so that we can compare them all, because what we're trying to find is the unknown substance. So we have carbon. We have 1.95 moles of that. We have hydrogen. We have 4.86 moles of that. And then we have oxygen, and we have 2.92 moles of that. So using those 3 numbers, let's put the smallest one on the bottom, because when we make a ratio and we divide, what we're really doing is kind of changing that denominator to 1, and so it makes it easier for us to compare. So we're going to start with hydrogen. We're going to compare hydrogen to carbon. So hydrogen goes on top and carbon goes on bottom. So for our carbon, that's 1.95, and for hydrogen, that's 4.86. And when we simplify that ratio, remember our carbon and hydrogen are still there, but our hydrogen our carbon becomes like as if it's 1. So 4.86 divided by 1.95. All right, so this one, we get 3 significant digits to keep, so 2.49. 2.49. Now let's do our oxygen. So we're going to compare oxygen. We're going to keep the carbon on the bottom. And so our carbon will still go down here. I should probably put little things. These aren't really like units. They're just to keep me straight so I can remember what's happening. So I still have carbon on the bottom. And it will become a 1. And oxygen is on top, 2.92. So this will still be oxygen over here on top. All right, so 2.92 divided by 1.95. And that's 1 point, and it rounds up to 50. So 1.50. So there's our ratio. Now these are not really like pretty whole numbers. You can't say I have 2.49 hydrogen atoms for every 1 carbon atom, or I have 1.50 oxygen atoms for every carbon atom. So to deal with this, we really need to multiply this up by something so that it makes it easier to see, because we can't put CH 2.49 O 1.50. That just wouldn't look right. And so what we're going to do is we're going to just multiply everything up to make it bigger. So since both of these kind of end in something that looks like 0.5, the 2.49 would round to that. It means we have halves going on. And so if we multiply by 2, that would fix it, and we'd get a bigger number. Let me finish with a different color so I don't have to keep switching. So let's multiply this by 2 on the top and 2 on the bottom. So 2.49 times 2 is going to become pretty close to 5. I guess I should actually do it for real. 2.49 times 2. All right, so 4.98. So 4.98. So that's how many hydrogen we have compared to 1 carbon. That's a lot more normal number. We can see that that's really close to 5, and so 5 is what that one's going to be. For this other one, we're going to do the same thing. We're going to multiply the top and the bottom by 2. Oh, shoot, sorry. That should have been a 2. So 1.50 becomes 3.00, and the bottom becomes a 2, and that's how many oxygen atoms we have compared to a carbon atom. So if we line these 3 up, and that's terrible looking. So C, H, and O. So our C is the bottom both times, and it has a 2. Our H is really close to 5, and our O is 3. So I just had to round that number up. You could mix those elements in a different order, and it's not wrong, it's just not standard. This is the standard order, but if you get them in the wrong order, I don't expect you to know at this point which order is most common, or which order you would most likely have. So the reason we couldn't stop here finding our ratios is because those just aren't close enough to a real integer, and so we had to unsimplify our fractions or make our ratios be something different so that it was closer to an integer. So right here we have numbers that are both close to integers. I mean, 3 basically is, but 4.98 is just close to an integer, and we can work with that. We know that the ratio of the hydrogen and the oxygen to the carbon means that when the carbon is 2, the hydrogen and the oxygen have the numbers, or close to numbers, of what they have in that ratio. That was kind of a long one and kind of a convoluted one, so if you didn't totally follow everything, you may want to look over it again, but as we go through future examples, at least for the next few chapters, we'll kind of move away from this a little bit, and so it won't continue to be this hard. In fact, I think the next chapter has easier problems than this one.